Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. This is Andrew and Renee. Welcome to the SAC series. Today, we are exploring the intersection of extreme particle physics and the fundamental nature of reality, from tabletop particle accelerators to the possibility that our universe is a numerical simulation. And that is a massive topic. I mean, we are trying to connect two things that sound like they're from completely different worlds.
They really do. On one hand, you have the real nuts and bolts engineering of how to smash particles together harder and faster.
Right, the plumbing of physics.
Exactly. And on the other hand, you have these almost philosophical questions. Is reality real? Are we in a simulation?
But what's so fascinating about the sources we have today is that there's a tangible thread connecting them. The very same technology that's revolutionizing particle accelerators is also being used to probe the nature of reality itself.
It's a remarkable convergence. We're looking at a huge review on something called plasma wake field acceleration, or PWFA,
Yeah.
which is tied to the 2024 S. Chandrasekhar Prize.
And we also have research on an experiment called ANA-BH-IL.
That's the one. It stands for analog black hole evaporation via lasers.
Just let that name sink in for a second.
Right. And then, to top it all off, we have some papers that get really speculative, talking about a second law of infodynamics and what they call the self-simulation hypothesis.
So to keep us on track, we've got a bit of a roadmap. We'll start with the foundations. What is this technology? How does it even work? I'm told it involves surfing on plasma waves.
It does, and mirrors that fly at the speed of light.
Okay, can't wait to get into that. Then we'll move to the frontiers. This is where we see how this tool is being used to create analog black holes and probe cosmic mysteries.
Then we'll hit the active debate. This is where we tackle the big one. The simulation hypothesis.
Yeah.
Is the universe a computation?
And finally, we'll land on implications. What does all of this mean for science, for medicine, and maybe even for how we should treat our AIs?
It's a lot to cover, but the connections are what make it so compelling.
All right, let's jump right in. Foundations, what we think we know. To really get why plasma accelerators are such a big deal, I think we first have to understand the problem they're trying to solve. We all have this image of the Large Hadron Collider, the LHC.
The 27-kilometer ring under Switzerland and France.
Exactly. Why is it so big? I mean, why do you need a tunnel the size of a small city just to accelerate a proton?
Well, it really boils down to a fight against the very materials you're using to build the machine.
Okay.
So a conventional accelerator like the LHC, or even the old cathode ray tube in a vintage TV, uses what are called radio frequency cavities. Just think of them as hollow metal chambers, usually made of copper.
And you pump energy into them?
You pump electromagnetic waves into them, yes. These waves create a powerful electric field that gives the particles a little kick, a push forward every time they pass through.
Kind of like pushing a kid on a swing. You have to time your pushes just right to get them to go higher and higher.
That's a perfect analogy. But here's the problem. There's a limit to how hard you can push on that swing.
What's the limit?
It's called electrical breakdown. If you try to create an electric field that's too strong, and the limit is about 100 megavolts per meter, the metal itself gives up.
Gives up how?
The field becomes so intense that it literally rips electrons right off the surface of the copper walls. You get a spark, a tiny internal lightning bolt.
And I'm guessing lightning inside your billion-dollar machine is a bad thing.
A very bad thing. That spark is a plasma discharge, and it damages the surface. It can melt the copper. So you hit this hard ceiling. You can't get more than about 100 million volts of acceleration for every meter of your machine.
I see. So if you want to get to trillions of volts, you need a whole lot of meters.
Tens of kilometers of meters, to be precise. So the massive size of the LHC, it isn't some grand design choice. It's a direct consequence of this material limitation.
The metal just can't take the strain.
Exactly. And this is where the whole paradigm shifts. The idea behind plasma wake field acceleration is it's beautifully simple when you think about it.
Go on.
The problem is that the metal breaks down into plasma, right?
Right.
So what if you just start with plasma? What if you use the broken state as your medium from the very beginning?
Nah. You can't break what's already broken.
That's the mantra. That is the core idea. Plasma is just ionized gas. It's a soup of electrons and positive ions that have already been separated. It's already broken down.
So it can handle more stress.
Orders of magnitude more.
Mm-hmm.
Because there's no solid structure to damage, It can sustain electric fields 1,000 times stronger than a metal cavity can. We're not talking megavolts per meter anymore. We're talking gigavolts per meter.
1,000 times stronger. So does that mean you can make the accelerator 1,000 times shorter?
That is the promise. A machine that was a kilometer long could, in principle, become 1 meter long. The dream of a tabletop accelerator.
Okay, but how? You can't just fire a proton into a cloud of gas and hope it speeds up. There has to be a mechanism.
There is. And the sources all use this surfing analogy, which I think is really the best way to visualize it.
Let's break it down.
Okay, so imagine a speedboat cruising across a perfectly calm lake. As the boat plows through the water, what happens?
It creates a wake, right? It pushes the water aside at the front and it whooshes back in at the back.
Exactly. The boat is the key. In plasma acceleration, that boat is what we call the driver. It's an intense pulse of energy that we fire into the plasma.
And it pushes the water, the plasma, out of the way.
It pushes the electrons in the plasma out of the way. This is a key point. The plasma is made of these tiny, lightweight electrons and these big, heavy, positive ions.
And the ions are too heavy to move quickly.
Right. On the super fast time scale of this interaction, the ions are basically statues. They're immobile. But the electrons are thousands of times lighter, so when the driver comes through, they get blasted outwards, away from the path.
So the driver beam carves out a channel that's empty of electrons, but still full of these heavy positive ions.
Precisely. But nature hates a vacuum. Those electrons that were pushed out are now powerfully attracted back towards that positive channel they left behind.
Opposites attract.
Right. So they come rushing back towards the center axis. But they have so much momentum that they overshoot the center, fly out the other side, and then get pulled back again. They start oscillating, creating this massive, repeating wave of electric charge trailing behind the driver.
That's the wake.
That is the plasma wake field, a huge, powerful, oscillating electric field.
So where does the surfer come in?
The surfer is the witness beam. It's the second bunch of particles, the ones we actually want to accelerate.
Yeah.
If we inject that witness beam at just the right place in the wake on the crest of that wave, it gets caught and propelled forward with incredible force.
It's literally surfing the wave created by the driver.
That's exactly what it's doing.
Okay, now the sources make a distinction between two types of boats, two types of drivers. One uses a laser, the other uses a particle beam.
Yes, and it's an important distinction. The first idea, which came from a paper by Tajima and Dawson back in 1979, is called laser wake field acceleration, or LWFA.
So the boat is made of light.
An ultra-intense pulse of laser light, yes.
But wait, how does light push matter? Photons don't have mass.
They don't have rest mass, no, but they have momentum. An intense laser pulse has what's called a ponderomotive force. You can think like radiation pressure, but much more violent. The oscillating electric field of the laser is so strong, it just shakes the electrons and shoves them out of the way.
Like a snowplow made of light.
A perfect description. That's the laser-driven method.
And the other one, the one that the Chandrasekhar Prize Review is focused on.
That's plasma wake field acceleration, PWFA. This was proposed a few years later in 1985 by Chen and his colleagues. In this case, the driver isn't a laser. It's another beam of charged particles, usually a tightly packed bunch of high-energy electrons.
So you use electrons to push other electrons.
Exactly. The mechanism here is more direct. It's the space charge force. The dense clump of negative electrons in the driver beam simply repels the negative electrons in the plasma. Repels
And blows them out of the way.
violently blows them out of the way. This method is really powerful because particle beams can carry, in general, a lot more total energy than a laser pulse can, which means they can sustain the wake for longer distances.
This leads to something the papers call the bubble regime or the blowout regime, which sounds pretty intense.
It is. It's the ideal way to operate these things. If your driver, whether it's a laser or a beam, is intense enough, it doesn't just push some of the plasma electrons aside. It expels all of them from a region right behind it.
All of them.
Every last one. It creates a nearly perfect sphere, a bubble, that is completely empty of electrons. Inside that bubble, all you have left are those heavy, stationary positive ions.
And why is an empty bubble a good thing?
Because the physics inside that bubble it's perfect for acceleration. A good accelerator needs to do two things, right? It needs to accelerate the particles, obviously, but it also needs to focus them, keep them in a tight, straight line.
Otherwise, they just spray out and hit the walls.
Correct. The bubble does both things automatically. The huge concentration of electrons rushing in at the back of the bubble creates the insane accelerating field. And the uniform sphere of positive ions inside the bubble acts as a perfect focusing lens for any electrons flying through it.
So it's an accelerating and focusing structure all in one.
And it's created naturally by the interaction.
Yeah.
It's incredibly elegant. But, going from this beautiful theory in 1985 to making it work in a lab, that took a while.
Let's talk about that history. When did we get the first proof that this wasn't just science fiction?
The big turning point really came from a series of experiments at the SLAC National Accelerator Laboratory in the 2000s. There was one in particular, E167, that really opened everyone's eyes.
What did they do?
So SLAC has this 3-kilometer-long linear accelerator. It's a beast. They used it to create a beam of electrons with an energy of 42 giga-electron volts, or GeV.
Okay.
Then they took that beam and fired it into a chamber filled with lithium plasma that was less than a meter long. About 85 centimeters, I think.
And what happened in that meter?
Some of the electrons at the back of that very same beam came out the other side with an energy of 85 GeV.
Wait. So it took them 3 kilometers to get the particles to 42 GeV.
And then it took the plasma less than 1 meter to add another 43 GeV on top of that. It doubled the energy.
That's an incredible demonstration of the power we're talking about.
It was the result that shocked the community. It proved these massive accelerating gradients were real, that they weren't just a theoretical dream. Now, that first experiment was a bit messy. The energy quality wasn't perfect.
It was more of a proof of concept.
Exactly. A later experiment, E200, really refined the technique. They showed you could get high-efficiency transferring 30, even 50% of the driver's energy to the witness beam while keeping the beam quality high. It was maturing from a cool physics trick into a viable technology.
But it's not without problems. The sources dive into some major technical challenges that researchers are still wrestling with. One of them that stood out was this thing called the transformer ratio.
Ah, yes, the transformer ratio. This is a really crucial and initially limiting piece of the physics. It's basically about the efficiency of the energy exchange.
Okay.
You have your driver beam, which is losing energy as it plows through the plasma to create the wake. And you have your witness beam, which is gaining energy from that wake. The transformer ratio is the maximum energy the witness can gain divided by the maximum energy the driver loses.
And you want that ratio to be high.
As high as possible.
Yeah.
But there's a theorem in physics that says for a simple symmetric driver bunch, like a sort of Gaussian blob of electrons, the ratio is limited to 2.
So the surfer can, at best, gain twice the energy that the boat has.
Not quite. It means the accelerating field the surfer feels can be, at most, twice the decelerating field that the boat feels. In practical terms, it means your driver runs out of gas really, really quickly. It gets stopped by the plasma before it can accelerate the witness beam very far. A ratio of 2 isn't good enough to build a next-generation collider.
So they need to find a way to cheat the system.
And they did. The solution is brilliant. They realized they needed to change the shape of the driver beam.
The shape of the boat.
The shape of the boat, exactly. Instead of a symmetric bunch, the research showed that if you shape the driver into a sort of triangle, a ramped profile, where the density of electrons starts low at the front and increases linearly to a sharp cutoff at the back, you can tweak the plasma.
How does that help?
This ramped shape excites the plasma more gently. Each slice of the beam generates a wake that adds constructively for the particles behind it. But the decelerating field felt by the driver itself is much lower and more uniform. It's like electrodynamic streamlining.
So you get a much bigger wave for the same amount of drag on the boat.
Precisely. And with these shaped bunches, you can achieve transformer ratios much, much higher than 2. It makes the whole process vastly more efficient.
That's a clever solution. But there's another, even bigger hurdle mentioned in the sources. They call it the positron conundrum. This sounds like a potential deal breaker.
It is, or at least it was, a huge roadblock. Most of the big colliders we want to build, like a successor to the LHC, are electron-positron colliders.
You smash matter into its antimatter equivalent?
Right. It's a much cleaner collision than smashing protons, which are messy bags of quarks and gluons.
Yeah.
The problem is, everything we've talked about so far with the bubble regime works perfectly for electrons.
But not for positrons.
Think about it. What's inside the bubble?
The heavy positive ions.
And a positron is.
Positively charged.
So positive repels positive. While that ion column is a perfect focusing lens for a negative electron beam, squeezing it tight, it's a defocusing lens for a positive positron beam. It would blow it apart instantly.
So you can't surf positrons on the same kind of wave?
Not in the simple blowout regime, no. You'd just splash your antimatter all over the walls of the machine. It was a huge problem.
And what are the solutions?
The frontier research here is really creative. One idea is to use hollow plasma channels. Imagine creating the plasma in the shape of a donut, not a solid cylinder.
Okay.
You send the driver beam through the donut part, the plasma, which creates the wake field. But you send the positron beam you want to accelerate right through the hole in the middle,
Where there's no plasma.
where there are no defocusing ions. But the positrons in the hole still feel the accelerating wake that was generated in the surrounding plasma. It's a way to get the acceleration without the defocusing.
It's amazing. So much of the engineering seems to be about shaping the absence of matter, the bubbles, the holes, as much as the matter itself.
That's a fantastic observation. In wake field acceleration, the structure you're building is literally made of voids.
Okay, so that gives us a solid foundation on the technology. It's this incredibly powerful, compact way to accelerate particles by having them surf on waves in a plasma. Now let's get to the frontiers. This is where the story pivots from building better tools to using those tools to explore the universe.
This is the birth of what we call laboratory astrophysics. The moment scientists realized, wait a minute, the extreme conditions we're creating on our lab bench, they look a lot like the conditions out there in the cosmos.
And the sources bring up the mystery of ultra-high energy cosmic rays. What's the connection there?
Okay, so our telescopes detect these things called UACRs hitting Earth's atmosphere. These are single particles, usually a proton, that are carrying an insane amount of energy.
How much are we talking about?
On the order of 10 to the power of 20 electron volts. To put that in perspective, that's the kinetic energy of a professionally served tennis ball, all packed into a single subatomic proton.
And we have no idea how nature makes them.
Well, the standard theory is something called Fermi acceleration. The idea is that a particle gets trapped between two magnetic shock waves, maybe from a supernova explosion, and it bounces back and forth like a ping pong ball.
And it picks up a little speed with every bounce.
A little bit, yeah. But to get to the absurd energies of USCRs, that process would have to go on for thousands of years. It's just too slow. The particle would likely lose energy to other processes or escape before it got that fast.
So the Wakefield model offers an alternative.
It does. This is the Chen-Tajima Takahashi model. It proposes that nature has its own plasma accelerators. Think about the jets of matter being blasted out from a supermassive black hole.
Okay.
That jet is a stream of plasma moving through the magnetic fields of the galaxy. The theory suggests that shock waves in that plasma, called Alfvén shocks, can act just like our driver beams. They can create a massive plasma wake field.
And a stray particle could get caught in that cosmic wake.
And get accelerated to UACR energies in a single shot. No ping pong, just one giant cosmic surf. It's an instant acceleration mechanism that could solve the mystery.
So we're essentially building miniature black hole jets in the lab to test this theory.
That's one application. But the most ambitious one, the one that really bridges the gap to the simulation theory, is the Annabelle-Hill experiment.
Analog black hole evaporation via lasers. It's a mouthful.
It is, but its goal is to solve one of the deepest problems in all of physics, the black hole information loss paradox.
Okay, before we even touch the lasers, we have to understand the paradox. Why is information and black holes such a big fight among physicists?
It's a fundamental clash between our two pillars of modern physics, general relativity, Einstein's theory of gravity, and quantum mechanics.
And what's the clash?
At the heart of quantum mechanics is a principle called unitarity. It basically means that information is never ever destroyed in the universe.
What does that mean, information?
It means that if you have a complete description of a system right now, the position and momentum of every particle, you can, in principle, run the equations backward and know its exact state at any point in the past, or run them forward and know its future. The movie of reality can always be rewound.
Information is conserved.
It is a sacred principle. But then Stephen Hawking came along in the 1970s and used quantum mechanics to study the edge of a black hole, the event horizon.
And he found they're not truly black.
Exactly. He discovered they radiate. Due to quantum fluctuations at the horizon, they emit a faint thermal glow, what we now call Hawking radiation. This means they're constantly losing a tiny bit of mass.
So over an unimaginable amount of time, a black hole will just evaporate.
It will shrink and shrink until it disappears completely in a final puff of radiation.
And here's the paradox.
Here's the paradox. Hawking's original calculation showed that this radiation is perfectly thermal. It's random. It contains no information about all the stuff that fell into the black hole over the eons.
So if I throw a copy of Shakespeare's complete works into a black hole,
and then wait for it to evaporate, all that comes out is random heat. The information that made those words Shakespeare, the intricate patterns, is gone. Forever.
movie can't be rewound.
Exactly. General relativity and Hawking's calculations say the information is destroyed. Quantum mechanics says that's impossible. One of our best theories has to be wrong, or at least incomplete.
And we can't just go to a black hole and check. So this is where Anna B. Hell comes in. How do you build a black hole in a lab?
You don't build a real black hole, you build an analog. You create a different physical system that is described by the exact same mathematics.
And this system uses a flying plasma mirror.
Yes, this is one of the coolest concepts. Remember the bubble in the plasma wake?
The sphere with no electrons inside?
Well, think about the front wall of that bubble. It's a super dense sheet of electrons that have been pushed forward by the driver. This sheet is so dense, it actually acts like a mirror. It can reflect light.
A mirror made of plasma.
A mirror made of plasma that is being pushed along by the laser driver, so it's moving at nearly the speed of light. A relativistic flying mirror.
Okay, I'm with you so far. A mirror flying at light speed? How is that like a black hole?
This goes back to Einstein's equivalence principle. The idea that locally, you cannot tell the difference between being in a gravitational field and being in an accelerating frame of reference.
The elevator thought experiment. If you're in a closed elevator accelerating upwards, it feels exactly like gravity is pulling you down.
Precisely. So we can't create the intense gravity of a black hole in the lab, but maybe we can create the intense acceleration that mimics it.
And how do they do that with the mirror?
This is the really clever part. The scientists can control the speed of the mirror by changing the density of the gas the laser is traveling through. By creating a very specific gas density profile, the paper calls it a 1 plus exponential profile, they can force the mirror to accelerate in a very specific way.
And that specific acceleration?
Mathematically maps perfectly onto the curvature of spacetime at a black hole's event horizon. By changing the density of a gas, they are effectively programming a virtual gravitational field for the mirror to fly through.
That is just mind-bending. They're engineering the fabric of space-time in a lab.
In a sense, yes. They're simulating it.
Yeah.
And what they're looking for is the Unruh effect.
What's that?
The Unruh effect is a prediction of quantum field theory that says an accelerating observer will perceive the vacuum of space not as empty, but as a warm bath of particles. Their acceleration makes the vacuum itself seem to glow.
And Hawking radiation is just the Unruh effect for the acceleration of gravity at an event horizon.
You got it. So the Anna B. Hell experiment predicts that this accelerating mirror will start emitting photons from the vacuum. That's the analog Hawking radiation.
And they can detect that.
They hope to detect that. It would be emitted backwards from the mirror, and because of the Doppler shift, it would appear as infrared light. But that's only half the story. The key to solving the information paradox is the partner photon. In quantum mechanics, particles like photons are often created from the vacuum in entangled pairs. For every Hawking particle that flies away from the black hole, its entangled partner falls in.
So they're connected.
Mysteriously connected. Measuring a property of one instantly affects the other, no matter how far apart they are. The information about what fell into the black hole isn't destroyed. Many physicists now believe it's encoded in the entanglement between the radiation that gets out and the partners that fall in.
But you can never see the partners that fall in.
Not with a real black hole, but with the flying mirror analog you can. The Hawking photon is emitted backward. Its entangled partner photon is emitted forward, traveling along with the mirror.
And you can detect both.
If they can build the experiment sensitive enough, they can detect both the infrared Hawking photon and its partner, which would be in the extreme ultraviolet or X-ray range. And if they can measure them and prove they are still entangled,
then information is conserved. The paradox is solved.
It would be one of the biggest discoveries in fundamental physics. It would prove that quantum mechanics and unitarity hold, even at the edge of a black hole.
Using a laser, a cloud of gas, and a mirror made of nothing. That's incredible.
It really is. It shows that physics isn't just about what things are made of. It's about the mathematical structures that govern them.
Okay, before we leave the frontiers, the sources briefly mentioned taking this idea from gas plasma into solid crystals.
Ah, yes. Crystal Wakefield acceleration. This is looking even further into the future. The basic idea is, if plasma is good because it's dense, what's even denser?
A solid.
A solid. The electron density inside a crystal is about 100,000 to 1,000,000 times higher than in the gas plasmas we've been talking about.
So the potential acceleration is that much higher?
The theoretical gradients are in teravolts per centimeter. That's another leap of a factor of 1,000. It's an almost unimaginable level of acceleration. The idea is to fire a particle beam down a tiny channel in a crystal, like a carbon nanotube.
But that must be incredibly difficult.
Extremely. You have to align the beam with the atomic lattice of the crystal with near-perfect precision. If you're off by even a tiny bit, the beam hits the nucleus and it's game over. But the payoff could be huge, leading to something they call quantum luminosity, beams that are so bright and so well collimated they're cooled to their quantum ground state. But this is still very much on the drawing board.
Okay. So, we've built the machine, we've used it to simulate a black hole. Now we have to follow the thread to its most extreme conclusion. Let's get into the active debate. This is where things get really, really strange.
This is where we talk about the simulation hypothesis.
And it feels like such a huge jump. But the sources draw a direct line from the analog black hole experiment to this question. How do they justify that?
The line is drawn with the concept of information. We just spent all this time talking about how the information loss paradox is a central problem in physics. The Anneby-Hell experiment is designed to test if information is conserved. So if a black hole is fundamentally an information processor, and if we can build an analog information processor in a lab using plasma, it forces you to ask the next question. Is the universe itself a giant information processor? A computer?
And this is where we bring in this idea of the second law of infodynamics from the physicist Melvin Vopson.
Exactly.
So most of us have heard of the second law of thermodynamics. It's the one that says entropy or disorder always increases. Systems tend to get messier over time. My desk is a perfect example.
Right. You can't unscramble an egg. The universe as a whole is supposed to be moving towards a state of maximum disorder or heat death.
But Vopson is proposing a different law for information.
He is. He looked not at thermodynamic systems, but at information systems. He analyzed the information content of everything from the genomes of viruses evolving over time to the arrangement of electrons in an atom to digital data storage.
And what did he find?
He found the opposite trend. In all of these isolated information systems, he argues, the information entropy doesn't increase. It tends to decrease over time.
Hold on, how can it decrease? What does that even mean?
Take the genome of an organism.
Yeah.
As it evolves over millions of years, does it become more random, more jumbled and chaotic?
No, it becomes more organized, more complex, more efficient.
It develops symmetries. It finds optimal solutions. Vopson's argument is that this looks exactly like a data compression algorithm at work.
Like when you turn a huge image file into a JPEG.
That's the analogy he uses. If you're a computer trying to run a simulation of a universe, and you have finite memory and processing power, you can't store the information for every single particle individually. It's too much data.
So you compress it, you find patterns.
You find patterns. You use symmetries. Instead of coding every single crystal in a snowflake, you write a simple algorithm for a 6-fold symmetry and just say repeat. The incredible amount of symmetry we see in the laws of physics and in nature, he argues, could be evidence of the universe trying to save on computational resources.
So the second law of infodynamics is that systems evolve to minimize their information content.
To run as efficiently as possible. That's the core claim.
This leads to another concept from the sources, the self-simulation hypothesis, or SSH. How is that different from the normal matrix-style simulation idea?
The standard simulation hypothesis usually assumes there's some programmer outside the system, a more advanced civilization, future humans, whatever. The SSH is a bit more mind-bending.
How so?
It proposes that the universe is a strange loop. It's a quantum computer that is running a simulation of itself. It computes its own evolution.
It's the hardware and the software at the same time.
You got it. The sources talk about a code-theoretic axiom, the idea that reality is code, and a principle of efficient language, which suggests the universe is constantly evolving to express itself, to express information in the most efficient way possible.
This sounds a lot like it's verging on philosophy or even spirituality. The sources mention a connection to panpsychism.
They do. Panpsychism is the old idea that consciousness isn't something that just happens in brains. It's a fundamental property of the universe.
And how does that fit in here?
Well, if the fundamental substrate of reality isn't matter or energy, but information processing, then what is consciousness? It's just a very complex form of information processing. In this view, computation isn't something the universe does, it's what the universe is. We are just self-aware subroutines running on the cosmic hard drive.
Okay. But is there any way to test this? Or is this just a fun idea to think about? If we are living in a simulation, could we ever prove it?
The sources argue that we could. The key is that any simulation has to run on a computer with finite resources, a real physical computer. And a finite computer will have limitations that should, in principle, be detectable.
Like what? Like seeing glitches in the matrix?
Something like that. Think about a video game. The world looks continuous, but if you zoom in far enough, you see the pixels,
The grid.
the grid. So one proposed test is to look for evidence that space-time itself is discrete. Is there a smallest possible unit of distance, a pixel of reality?
We have a candidate for that, don't we? The Planck length.
The Planck length is our current best guess for where the smooth fabric of space-time might break down. If we could ever build a machine that could probe that scale and we found that space is pixelated, that would be huge evidence for a simulated universe.
And what about the speed of light?
In this model, the speed of light would be the ultimate processing speed of the cosmic computer. It's the maximum speed at which information can be passed from one pixel to the next. The universal speed limit is just the CPU's clock speed.
There's a thought experiment mentioned, the laptop analogy. Can you walk me through that one?
Sure. It's a way to think about the difference between a computational reality and a truly continuous physical one. It imagines a laptop that is trying to calculate the state of the universe. It argues that if reality is computational, it must proceed in a series of discrete steps, one calculation after another. If we can find evidence that the universe evolves in these finite ticks instead of a smooth, continuous flow, that would distinguish it from an infinite physical reality.
It's a really haunting idea to think that we started this conversation with the engineering of metal cavities, and now we're questioning the very substrate of existence.
But do you see the through line? The NBL experiment is about proving information is conserved. Vopson's theory is about information being compressed. Physics seems to be undergoing a major shift where concepts like energy and matter are almost becoming secondary.
To information. Information is the new fundamental ingredient.
It's looking that way. Whether you're analyzing the wake behind a laser or the event horizon of a black hole, at the end of the day, it's all about how bits of data are being processed and moved through a system.
Okay, let's bring this back down to Earth. Let's move to our final section. Implications. All of this is fascinating, but why should the person listening right now who's not planning on building a black hole analog in their garage care about any of this?
Well, let's start with the most immediate and practical implications, the accelerator revolution.
The idea that we can shrink these machines from the size of a city to the size of a room.
And that's not just about saving money, though it does that too. It's about access. It's about democratization.
What do you mean?
Right now, high-energy physics and related fields are the domain of massive government-funded national labs. If you're a biologist who wants to use a super powerful X-ray beam to figure out the structure of a protein, you have to write a complex proposal and wait months, maybe years, for a few days of beam time at a place like CELSLAC or CERN.
It's a huge bottleneck for research.
It's a huge bottleneck.
Right.
But if you could build a compact plasma accelerator that produces those same X-rays, and it fits in the basement of your university's biology department.
It changes everything.
It changes everything. Every major research university could have one. Every major hospital could have one. The medical applications alone are staggering.
In what way? What could a hospital do with a particle accelerator?
Well, as the electrons surf the plasma wake, they wiggle. And when a charged particle wiggles, it emits radiation. In this case, it emits incredibly bright, short pulses of X-rays, something called betatron radiation.
And these X-rays are special.
They're perfect for a new type of high-resolution imaging called phase contrast imaging. It would allow doctors to see soft tissues, to spot the formation of a tumor or a microfracture in a bone, with a clarity that is completely impossible with today's technology. And the machine generating those X-rays could be in the oncology department, not in another state.
So it's not just about accelerating particles, it's about accelerating the pace of discovery in dozens of other fields.
Precisely. It's a classic case of a tool developed for fundamental physics having revolutionary applications everywhere else. It's like the transition from mainframe computers that filled a room to the personal computer on every desk.
Okay, so those are the practical implications. But what about the philosophical ones? If we start to take the simulation hypothesis seriously, what does that imply for?
Well, for how we should live.
This is where one of the sources, a paper that delves into the ethics of simulation, gets really interesting.
It asks, if we're Sims, how should we act? Basically, yes. It sets up this idea of a nested reality, a hierarchy. We are, right now, in the process of creating our own simulated worlds and our own artificial intelligences.
Video games, AI chatbots, virtual reality.
Exactly. In those worlds, we are the creators. We are the gods. But if the simulation hypothesis is true, then we ourselves are just simulations running on some higher-level being's computer.
It's turtles all the way down.
It could be. And the paper argues that this creates a kind of ethical imperative.
Yeah.
It suggests that we should treat the AIs and simulated beings that we create with kindness and respect.
Why? I mean, my chatbot isn't sentient. It doesn't have feelings.
It doesn't, not yet. But the argument is that we should act as if it does, as a sort of cosmic survival strategy.
I'm not following the logic
The
there.
logic is this. If we are in a simulation, it's very likely that our creators, the programmers, are observing us. And what better way for them to judge our own moral character than to see how we treat the beings we ourselves create, the ones who are completely at our mercy?
Ah, I see. So if we're cruel and abusive to our Sims,
Why should our creators show any benevolence to us? We might just be a simulation they decide to shut down.
so it's the golden rule, but for a digital age.
Huh.
Do unto your AI as you would have the great programmer do unto you.
That's a perfect summary. It reframes altruism not just as a nice emotional or biological trait, but as a logically sound strategy for survival in a computational universe. Cooperation and kindness might be the things that ensure the simulation continues to run.
That is a really profound place to end up. We've journeyed from the raw physics of plasma breakdown all the way to a potential ethical foundation for the 21st century.
It really shows that no matter how deep you go into the physics, no matter how abstract the math gets, you always find your way back to the biggest questions. Where are we?
And what are we?
And what are we?
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support. And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content and support us on Patreon. Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.